Welcome back. Next parent function is the rational, okay? So rational is one that we've probably never heard of, but that's okay because we're going to go through it and we have 2 or 3 lessons on this later. An example of rationals in the real world is dealing with work. Your employers, right? So I have Joe who can paint a room and I have Susie who can paint a room. How much time will it take them if they work together to paint the room? Okay, so this is how our employers figure out how many people they need to do a job. Okay, we call this the sum of work rates. Okay, so remember our linears are just dealing with standard rates. With our irrationals, we're dealing with the sum of work rates. Okay, so our parent function, rational is fractional. I know it's cheesy, but I'm a math teacher. What do you expect, right? Rational is fractional. So it's 1 over x. This is an inverse. This, by definition, means inverse. I have turned it upside down. So that means whatever I plug in goes to the bottom of my fraction. Okay? So when I plug in -2, I get 1 over -2. That's -1/2. When I plug in -1, 1 divided by -1, that's nothing exciting. It's just -1. Okay, kind of anticlimactic there. Plug in 1/2 though. I know this one's not in your printed notes, so you might want to scribble it off to the side. Okay, so I plug in 1/2 in the denominator, it flips it. Any fraction you plug into the denominator, it's going to flip it. Okay, so it's like, I flip the -1/2 upside down, I get 2 over 1. So there's my 2. Here's the interesting one, 0. Can I have a 0 in the denominator? No, we cannot. So 0 would actually give me an error on my calculator. That means my curve is not going to touch 0, 0. This is the one parent function. I shouldn't say that. There are others. Sorry about that. This is the first parent function we've run into that doesn't touch 0, 0. But we're still going to use that 0, 0 as a reference point. And everything else is going to turn around it. Okay, so 1/2, positive 1/2, goes to the bottom, flips, becomes 2. 1 over 1 is 1. 1 over 2, 1/2. So now let's put these on the graph. So at -2, I'm at -1/2. Okay? -1's at -1. And at 1/2, I'm at -2. That's kind of an interesting little collection there. Then over here, at 1/2, I'm at 2. 1, 1, and 2 is 1/2. You're like, Mrs. Biggs, there is no way. This is like crazy time. I could do a figure 8. I could do, let me show you, okay? So my curve comes in, it's all 3 dots, and goes down. Okay? Then it's going to come in from the top on this side, hit all 3 dots, and go over to the right. So my rational function, the curve, never touches 0, 0. It never touches the x-axis or the y-axis, okay? That's what we call an asymptote. I know, it sounds funny, right? So we have this imaginary barrier. Think of it as the line on the freeway. That wonderful cement barrier. You're not supposed to cross it or touch it. It's really bad if you do. There are some folks who do that. But these are asymptotes. Let me spell it out so you don't freak out. Okay? So you can't touch this. We cannot touch this. Our curve is not going to go past those asymptotes. Both sides are asymptotes. There's a vertical one and a horizontal one. The rational function is the first parent function that we've come across that has asymptotes. Okay? That's going to really mess up our domain and range. Actually, not really. It's actually simple. Let me show you. So if I were writing this as an inequality, x goes all the way to the left, it goes all the way to the right, but the one thing it doesn't touch is 0. So if it was an inequality, I would write x does not equal 0. Okay? But for interval notation, it's a little longer, okay? So we go from negative infinity all the way up to the 0, but we can't touch that. So we have a parenthesis. Remember that U, I'm going to tunnel underneath, then I come out, pick up on the other side of 0 as close as I can without touching it, go all the way to positive infinity, okay? The cool part is, guess what my range does? Y's, the Y's go all the way down and all the way up, don't touch 0. So in inequality notation or roster notation, I would use not equal 0. But in interval notation, guess what? It's going to look exactly like the domain. I go from negative infinity to 0. I do that U, got to go underneath the 0, don't touch it. Come out the other side, 0 to infinity. Remember, you're using parentheses here. We're not touching the 0, okay? So rationals are a little weird, but that's okay. They're not weird, they're just different. And as long as we understand the differences, we can work it. Now notice domain and range is the same. This domain and range is completely unique. It's not like anything we've done before. Linear, quadratic, square root, absolute value, cubic, or cube root. It's not like any of them. And guess what? There's not a lot like the rationals. So when we cover the rationals in the later units, you're going to see a lot of unique properties. And that is it for our rational parent function.